Good morning, geometry. Today we're going to get started with 5.1 continued. So you had your quiz on Monday on your first section of part 1. This is the second half of part 1. It's a pretty heavy vocab unit, so we split it up. So the first term you're going to learn today is concurrent lines, which is when 3 or more lines intersect at a common point. So right here we have concurrent lines. 3 lines intersect at this common point. A point of concurrency is that point at which the 3 lines intersect. So this right here would be a point of concurrency. So this is the point of concurrency. And then lastly, we have our circumcenter, which is the point where 3 perpendicular bisectors intersect. This point would actually also be our circumcenter in this picture, because I have a perpendicular bisector here, here, and here, and they're all intersecting right at that point. The circumcenter theorem tells us that the perpendicular bisectors of a triangle intersect at a point called the circumcenter that is equidistant from the vertices of the triangle. So what this tells us here is that GA is congruent. So I have, this tells me the perpendicular bisectors right here, perpendicular bisectors are equidistant from the vertices of the triangle. Okay, so these perpendicular bisectors are equidistant from the vertices of the triangle. So what that tells me here is that GA is congruent to GB, which is congruent to GC. These 3 pieces are all congruent by that circumcenter theorem. Next, we have the incenter, which is the point where the 3 angle bisectors intersect. So this is an angle bisector. It's cutting that angle in half. So is this, and so is this. This point where they intersect, that's our incenter. The incenter theorem tells us that the angle bisectors of a triangle intersect a point called the incenter that is equidistant from the sides of the triangle. So this point is equidistant from the sides, which makes all of these sides, these in red, all of these sides, yours might not be red when I print it out for you, but on the computer it's probably red. All of these red pieces would be congruent. So this incenter point is equidistant from the sides. If I said vertices, you would look to B and A, but I'm saying sides, so you want to go from here to the sides. So this means that DE is congruent to DF, is congruent to DG by that incenter theorem. So circumcenter tells us this point in the middle, this circumcenter, it has equidistant lines to the vertices. Incenter tells us from that incenter point, we have equidistant lines to the sides. Now we're going to flip to the next page and talk about a centroid. A centroid is the point where the medians intersect. Now you'll notice a lot of words are coming up here. When we talked about circumcenter, it mentioned perpendicular bisectors, which we talked about last class. Incenter talked about angle bisectors. Centroids now talking about medians. So it's bringing up that vocab from the first half of 5.1. Okay. So our medians, remember, come down, make a midpoint, which makes these two pieces equal. Okay, so do not forget that that is a median. So in black, what I'm highlighting here, these are all medians. And you can tell that because these pieces are equal and they've labeled that for you. Okay, so these are medians, which makes this middle point a centroid. Now the centroid theorem is a pretty interesting one. The medians of a triangle intersect at a point called the centroid that is 2/3 of the distance from each vertex to the midpoint of the opposite side. Now, I want you to write a few theorems down here. The first, whenever we do the centroid theorem, we're going to label a short piece, a long piece, and the whole piece. Those are just three things you'll hear me mention a lot, okay? So some formulas that will help you solve these is that the long piece divided by 2 equals the short piece. The short piece times 2 equals the long piece. And then lastly, this is 1, 2, 3, the whole piece times 2/3 should equal that short piece. So if you are someone who thinks visually, you may just like this explanation I'm about to give better. If you're someone who likes formulas, those are some for you. I kind of use a little bit of both here. So when you look at a centroid, okay, so if I look here and it tells me that QV is 4, so they're telling me this is 4. I want to look at this whole piece from Q to U, okay? If this is, when you look at those two pieces, I would ask you, okay, what's longer, QV or VU? And hopefully you would know QV is longer than VU. You can just tell by looking at it. So this is my long piece, VU is my short piece, and QU is the whole thing. So if the long piece is 4, okay, I can just divide the long piece divided by 2 to get the short piece. So 4 divided by 2 gives me 2. And then the whole piece, obviously, you just add the short and long together. So 4 and 2 would be 6. Okay, let's do another one together.